So, reminder about probability. We talked a little about examples of probability yesterday, and I gave a definition. I'm just going to repeat that definition, and we're going to play with it today. It's a measure of our belief that something will happen. And then the question is, how do we measure that belief? And there's a couple of different ways, and I classified them a little bit. We're gonna play more with those classifications today. So we played first with the simplest kinds of things, like flipping a coin, rolling a die, picking a card, and those kind of fall into a theoretical category. And to calculate a theoretical probability, we just have to know what are the possible outcomes. And then we have to know the favorable outcomes that we're looking for. We talked about outcomes in terms of events, and I mentioned the idea of a simple event, an event that can't be any simpler than it is. Like I flip a coin and I get a head. A head is a head. I roll a die and I get a 2. It's a 2. But I could roll a die and get an even number. Now an even number could be a 2, a 4, or a 6. So since it's multiple options, that's not simple. And theoretical probability is just looking at those outcomes and counting the favorable ones and counting all of them and then just dividing them. So it's this ratio. And the thing about theoretical is that we believe we know everything there is to know about the situation. So when I actually, let's switch cameras for fun. Where's that? Right there. Some stuff. All right, and let's see. Oh, I gotta turn off that background. Sorry, I forgot about that. We're gonna roll some dice. You see dice here, hopefully. Okay, just not zoomed in. And that's okay, we'll just wing it. Come on, Zoom. Okay, so hopefully you see a 5 and I rolled a 1. Now this green one here, what it means to know everything about this is that there's 1, 2, 3, 4, 5, 6 different numbers on it, right? And that one number is just as likely to appear when I roll it as another. So the outcomes are equally likely, right? So that would be knowing everything there is to know about this die. And again, I believe those things are true. Now I can see 6 different numbers, but how do I know like there isn't a little piece of lead right near the 1 so that when it rolls, more often the 1 will be down and the 6 will be up, okay? So, that's a possibility. So I'm believing that each outcome is equally likely, but again, that's a belief. I would have to test that belief somehow. But often with theoretical probabilities, we just think we believe it and we just go for it. So I could roll the pair of dice, and there I got 2 2s for a sum of 4. 2 6s for a sum of 6. Ooh, is something fishy going on here? 3 and a 5, sum of an 8. Okay, so lots of different things could happen. And, I have all kinds of die. I'm going to get another pair out here. So let's see, that's a nice one, and that's a nice one. And I like that one too. So like, let's roll these two. I get a 2 and a 5. I get a 5 and a 6. I get a 6 and a 5. I get a 5 and a 6. I get a 2 and a 5. Doesn't anybody notice anything interesting about these two red die that seem different than the other two? 6 and a 5. 6 and a 5. Interesting. 2 and a 5. 5 and a 6. Anybody see a pattern going on here? 5 and a 6. Where's my chat? Anyone chatting? Am I all alone here? You guys see what I'm doing?
Is one of them only a 5?
Okay, yeah. So one of these dice has only 5s on it. 5, 5, everywhere, a 5. Right? The other one has 6s and 2s. So I bought these dice in Las Vegas a couple years ago, and they are for playing craps or cheating at craps. So there's a pair that look identical that are perfect, right? And I could have the other ones up my sleeve and swap them out. And this one, I will get 11s, 12s, 7s, and those are all good numbers to get playing craps. So there's lots of ways you can have dice that don't have equally likely outcomes for the numbers on them. So this whole idea about, do we really know or do we just believe it for theoretical probabilities is an important idea. Let me switch back to the notebook. All right. So I keep trying to stress that probabilities are a measure of our belief. And even when we think we know something for sure, a lot of what we think we know, we really just believe it. But we believe it so strongly, we call it knowledge. Now, I'm not saying knowledge doesn't exist. It certainly does. There are some things that are certainly true. But again, we have to be careful about beliefs versus knowledge. And often with theoretical probabilities, they're based on beliefs. Belief that the coin is fair, just as likely to get heads than tails. Belief that the person flipping it can't rig it somehow. And I did know a guy who was a magician, and he was so good at flipping a coin, he was able to use just the right amount of flick, knowing that it was a head facing up on his thumb, that he could catch it with a head facing up. And it looked like it was spinning pretty good. He was just that practiced at that skill. Most of us aren't, right? So he was special in that regard. And then my dice were special in a different way. So theoretical probabilities. Not everything can be measured theoretically because there's some things we don't know. And that's when experimental probability comes into play. And with an experimental probability, we have to make these repeated trials of some experiment. And then after we do those repeated trials, we just count stuff up. And we just count, again, the favorable outcomes. So it's pretty much the same definition. Versus all total outcomes. Change that a little bit and write total outcomes from those trials. And so the example I gave last time of experimental probability was the throwing the dice. I mean, sorry, throwing free throws. That there are only two outcomes, but they're not equally likely. It depends on the individual. Maybe some individuals, they're just as likely to get it in as not. I was more likely to miss the other day. Some people are more likely to get it in when they throw a free throw. And then we could also do experimental probabilities with our dice. And I could just roll this over and over again and watch what happens. And the idea I was trying to give at the end of class the other day that we're going to play with today is the connection between theoretical and experimental called the law of large numbers. And that says for a large enough set of repeated trials that the experimental probability will be approximately equal to the theoretical probability. And then the question is how many is enough, right? So a large number of trials is what we're talking about here. And so that's what the second activity is going to be about, is just looking at our data so far for the spinner to see if that relates to the theoretical probabilities we're going to calculate for the spinner. So we're going to play a little bit more with theoretical probabilities first, and then we'll look back at experimental probabilities. And then there's a lot of probabilities that are kind of a mix between these two here. So at the beginning of class, Amanda asked if it was snowing where I am, because it looked like it was about to where she is, and it feels cold enough here. And let's check, I'm in Pendleton right now, the weather, and I have a 9% chance of precipitation. They're giving me a probability right here, and that changes throughout the day. So this says 9% chance of rain through 4 p.m. So new page, 9% chance of rain. So, you know, we have these phones, these computers that just predict these things for us, and this came from somewhere. So somehow somebody came up with this prediction right here. This is a probability. I got the idea of chance there. Chance is a probability. What does this mean? And how does it relate to the ideas of theoretical and experimental probability? So just think about that for a minute. What does 9% probability mean? And I'll talk about some interpretations of it. 9% chance of rain. So my young daughter asked, what does it mean there's a 9% chance of rain, Dad? Say, well, there's a 9% chance of rain. Well, I can't just repeat it, right? What the heck does that mean? I need to state that in a very different way that kind of gets at that idea.
Does that mean there's a 91% chance that it won't rain?
Yeah, but I don't know if that helps much, but that is true. If let's see, the opposite of raining is not raining, sure. Okay, so that's part of it.
The likelihood or probability that it's going to rain.
Okay, so all we're doing is replacing the word chance with probability or likelihood. That doesn't help either. So chance, probability, likelihood all mean exactly the same thing. What does this 9% mean? And it is true, if there's a 9% chance of rain, there's a 90% chance it won't rain. But let's strike that from the explanation also. 9%. Okay, so I'm gonna say it's probably not gonna rain, right? I could say that. And my daughter might be satisfied. Oh, okay, it's probably not gonna rain. What do you mean by probably? And I would say, well, probably not, in this case means 9%, but I'm doing this circle, right? 9% means probably not. What does probably not mean? Probably not means 9% chance. So we got to get more at it. So misinterpretations of this, right? We got this place called Pendleton here. And one misinterpretation I've heard of before is that this spot right here is 9% of Pendleton. It's going to rain there. It's not going to rain anywhere else, just that spot of Pendleton, right? That's like, no, that's not true. That's not what the 9% means. So that would be a misinterpretation of this probability. 9% chance of rain. It's going to 9% of the day. No, that's not what it means either. And what we have to do is kind of put this into either historical context or sci-fi context. So historical context is 9% of days similar to today in the past. It rained. So similar means, you know, same time of year, same weather conditions that led to this, that are around us, same barometric pressure, same wind direction, all these different things we look at for weather. That given 1,000 similar days, 90 of those 1,000 days, because 90 out of 1,000 reduces to 9 out of 100, right, which is 9%, it rained. And the other, right, how many are there? 910 days out of those 1,000, it did not rain. Now, do we actually have that many days that were similar? The answer is not really. It's a combination of actual historical data and computer models. So this 9% is a whole bunch of stuff. There is historical data. And then there are also these computer models where they try to generate computer simulations of days like today and see when does it rain, when doesn't it. So this is kind of a combination of experimental probability and some experimental / theoretical probability together that are leading to this prediction right here. The sci-fi version of this 9% right here is related to like an alternative universe theories, that there's all these other alternative universes out there where there's a me talking to you guys, but in that meeting, I didn't bring out my red dice that day, right? So it's a different reality because I made a slightly different decision earlier on. That I didn't misspeak something, that I didn't miswrite something. So every time a decision happens, the universe fractures into this other universe. And so there could be all these other universes parallel to this one with a whole bunch of yous and me's in them doing stuff. And if we grabbed 1,000 of those randomly, we would find that in 90 of those universes, it is raining right now. And in the other 910, it is not raining. So the 9% chance of rain is a use of probability. It's a little more complicated than just the theoretical or experimental, but it comes from these two together and a whole lot of science. All right, so essentially then we could go probability. There's actually like 3 versions of it. There's the theoretical probability, there's the experimental probability, and then there's the kind of educated guess probability, which is what this stuff is right here. Educated guess, which is a blend of the experimental and the theoretical with a whole bunch of science. So backing up just a little bit to play a little more with theoretical probability. Some other kind of situations we can come up with that are slightly different than the rolling the dice or the free throws kind of thing. This is my best drawing at the moment of a dartboard. And let's say my dartboard has a 1-foot radius. And then inside this dartboard, there is a special section that I would like to hit right in the middle here and say that special section, let's say it has a radius of 1/2 of a foot. Then I might want to know what is the probability of hitting the blue part if a dart is randomly hits the board. We still got to figure out what random means in simulation. So a dart randomly hits the board. What's the probability of hitting the blue section? And it still goes down to the same idea we had before. Probability is a ratio of favorable outcomes. Favorable over total. And so we just figure out how to measure those. And so earlier I said probability is a measurement, and measurement is always the hardest part. How do we measure this situation? Well, total, what do you think? How would I measure the total dartboard here? Suggestions? Circumference. So circumference would only be hitting the edge, so not circumference. You're on the right track though. Pi radius squared. Yeah, we need the area here, okay? So total for this, well, the radius is 1, I was thinking, so that would be pi times 1 squared. And then I just want to know, okay, I'm favorable as me hitting the blue part. And so the blue part would be pi times the radius, that would be 1/2 squared. So cleaning that up a little bit, the pi's would divide out. Number divided by itself is 1. 1 squared in the denominator is 1, and dividing by 1 is kind of boring. So really it all boils down to this part here. That would be 1/4. So it turns out that blue section is 1/4 of the whole thing. If the whole dartboard has a radius of 1 foot and the blue part has a radius of 1/2 of a foot. So I would have, if the dart always hits, but it hits randomly somewhere on the board, that I really don't have control over whether it hits the middle or the edge, that there's a 1/4 chance of hitting the blue section. And again, that was that random part. Now, usually people that throw darts have some skill, so they're pretty good at hitting like this part of the board or that part of the board or that part of the board. Getting like a smaller bullseye would be a little harder. But then, you know, in reality, there is a chance of not hitting the board. Okay. So we had a whole bunch of assumptions, some beliefs about this situation. And then once we could narrow down those beliefs, we can make a measure for that probability. So I think there's a 1/4 or 25% chance, given the conditions I started with here, that the dart randomly hits the board. So again, favorable over total, we just got to figure out how do we measure these things. So those are the basic ideas of probability. Now, these are all probabilities where one thing is happening. We throw one dart, we throw one free throw, we roll one die, we flip one coin. Let's take a look at multi-stage probabilities next. Oops, wrong way.